Welcome to the Deep Dive, the show where we take your sources, your research, your notes, and, well, we sift through it all to pull out the most important, insightful nuggets of knowledge just for you. Today, we're tackling one of those perennial challenges in economics and social sciences.
Yeah.
It's a really thorny one.
Yeah, I know the one you mean.
How do you actually figure out cause and effect when you just can't run a perfect randomized experiment?
Right. It's the million-dollar question, isn't it? Especially for researchers and, particularly for graduate students just starting out, wrestling with real-world data.
Exactly. It keeps people up at night.
It does, because look, in a perfect world, we'd always use a randomized controlled trial, an RCT. That's the gold standard for identifying causal impact, no question.
You'd have that luxury of perfect random assignment, treatment group, control group, clean comparison.
Perfectly clean, you could isolate the impact of whatever intervention you're studying, but, well, real life just isn't that neat, is it?
Not usually, no. Policies get rolled out, programs get implemented.
And who gets access, who's affected, it's often based on complex criteria. Definitely not random, often quite messy, actually.
So the crucial question becomes, how do we tease out the actual causal impact in those messy real-world scenarios where true randomization just isn't on the table?
And that's where we're focusing today.
Precisely. This deep dive is custom-tailored for you, the listener. We're zoning in on a really powerful quasi-experimental method designed to try and mimic that randomization we wish we had. It's called regression discontinuity, or RD.
A very clever approach.
We're going to systematically unpack the methodological side of RD. We'll get into precise definitions, use some analogies to make the core logic click, and ground it all with concrete, real-world examples from the materials you provided.
The goal is really to give you a clear step-by-step guide. How do you actually implement these statistical methods? What are the crucial checks, the diagnostics, the assumption validations you have to do?
And, critically important, how do you interpret the results? What do those coefficients actually mean in the context of real-world scenarios? We're aiming for a rigorous academic tone, perfect for graduate students, equipping you with a robust tool for your analytical toolkit.
And RD really does stand out. Its power lies in its potential to control for both observable and, crucially, unobservable variables.
That's a key distinction, isn't it, compared to other methods?
Absolutely. Think about something like propensity score matching. Very useful, but it primarily controls for things you can see and measure the observables. RD, because of its unique setup around that cutoff, gets at the unobservables too.
Those hidden factors, like motivation or innate ability, that can really muddy the waters in causal inference.
Exactly. And being able to account for those makes RD one of the most powerful causal inference techniques we have when randomization isn't an option. It gets us closer to a truly causal estimate.
Okay, so let's unpack this core concept then. Regression discontinuity. What is it at its heart?
Well, at its core, it's a regression-based method. It's designed specifically to identify causation by mimicking randomization, but only in a very specific kind of situation.
A surgical context, you said earlier.
Yeah, that's a good way to put it. It works by taking advantage of an eligibility threshold that's set somewhat arbitrarily on a continuous variable.
Okay, so you need two things there. A continuous variable and this threshold, this cutoff point.
Precisely. Imagine a scenario where access to some program or being affected by some policy isn't random at all. Instead, it's determined by hitting a specific point on a measurable scale, a sharp, clear cutoff.
Like an income level or a test score or maybe distance.
Exactly, those kinds of things. If you find that kind of setup, that's where RD becomes incredibly valuable.
And this ability to handle unobservables is what really sets it apart, you were saying, from, say, propensity score matching.
Right. Propensity score matching is great for balancing groups on things we can measure: age, education, income, whatever's in our data set. But what about the things we can't measure? Motivation, resilience, family support.
The stuff that might make someone more likely to succeed anyway, regardless of the program.
Exactly. Those unobservable confounders. PSM struggles with those. RD, because of how it focuses on that tiny window around the arbitrary cutoff, gives us a way to control for both the observables and those tricky unobservables. That's why it's considered such a robust method when its conditions are met.
Okay, let's drill down on this arbitrary threshold logic. That seems absolutely central.
It is. It's the whole engine of RD. So, first condition. RD is only applicable when access to the program or policy is determined by an eligibility criterion defined on a continuous variable.
So not categorical things like yes, no, or urban, rural. It has to be something that can take on a range of values.
Correct. Things like income, age, test scores, distance from a location, years of experience, landholding size, anything that runs along a continuous scale.
Okay, now the arbitrariness. Let's use that income example again. Say a government program gives cash transfers, but only to households earning less than $50,000 a year. Now, $50,000 is a nice round number. Policymakers like round numbers. But is it fundamentally meaningful in some deep economic sense? Why exactly $50,000?
Precisely. Why not $51,000? Or $49,500?
Or $50,001?
It feels kind of arbitrary, chosen for convenience maybe, rather than because there's some fundamental shift in household nature right at that point.
That's the key insight, the arbitrariness. It means that a household earning, say, $49,900 is probably not fundamentally different in all sorts of ways we can't even measure from a household earning $50,100.
Right. Their underlying characteristics, their motivation, their needs, probably very, very similar. They're neighbors on the income scale.
Exactly. And this is what we call the comparability principle. Because that threshold is arbitrary, those who are just eligible, the $49,900 household, are expected to be remarkably similar on average to those who are just ineligible, the $50,100 household.
They're incredibly close to the threshold, almost identical in many respects.
Yet, crucially, one group gets the treatment, the cash transfer, and the other group doesn't, purely because of where they fall relative to that arbitrary line. And that's what mimics randomization.
That's it. The similarity near the cutoff effectively mimics a randomized experiment, but only in that very narrow window right around the threshold. It's like nature or policy flipped a coin for the people right at the edge.
Let's take that microfinance example for farmers.
Okay.
Loans are only for those owning less than 10 acres.
Okay.
A farmer with 9.5 acres,
Okay.
probably very similar to a farmer with 10.5 acres, right? In terms of their skills, local conditions, maybe even their ambition.
Very likely, yes. Their day-to-day reality is probably almost identical.
But because of that 10-acre rule, only the 9.5-acre farmer gets the loan. The 10.5-acre farmer doesn't.
Right. Different treatment assignment based purely on being just either side of an arbitrary line.
So if we then look at their outcomes later, maybe farm productivity or income, any difference we see between those two groups right at the cutoff can be plausibly attributed causally to the loan itself.
Not to some underlying difference between the farmers, because we assume they were essentially the same to begin with, thanks to the arbitrary nature of the cutoff. It's as close to a natural experiment as you can get sometimes.
Okay, that logic is clear. So to formalize this a bit, especially for you listening and planning to use RD, let's nail down some key terminology.
Good idea. First, there's the eligibility variable. We usually call this S. That's the continuous variable we've been talking about: income, age, test score, land size, the one used to determine who's in and who's out.
You might also see it called the running variable or forcing variable or rating variable in different papers or textbooks, right?
Exactly. They all mean the same thing, that continuous variable driving eligibility.
Then there's the eligibility threshold. We often denote this as S star.
Right. S star is the specific value of S that defines the cutoff. If you're below S, you get the program. If you're above, you don't, or vice versa, depending on the rule. It's that critical dividing line.
Now, visualizing this really helps, I think.
Absolutely. The graphical intuition is very powerful for RD. Imagine you create a scatter plot. On the y-axis, the vertical one, you put your outcome variable, y. Let's say that's children's study time or maybe wages.
Okay.
And on the x-axis, the horizontal one, you put your eligibility variable, s. Maybe that's household wage or years of education.
So you plot all your data points, each household, each individual.
Right. And typically you'd expect to see some kind of general relationship or trend between Y and S across the whole range of S. Maybe wages tend to go up with education, or study time has some complex relationship with parental income.
But the key thing we're looking for in RD is what happens at the threshold, at S.
Exactly. If the intervention being studied actually has an impact, what we hope to see is a sharp jump or a discontinuity in the relationship between Y and S, right at that S point.
So the trend might be smooth on either side of the cutoff.
But right at the cutoff, the average value of Y suddenly shifts upwards or downwards. There's a visible break in the pattern.
That vertical distance of the jump, that's the effect.
That jump is the RD estimate of the treatment effect at the cutoff. Let's use that health clinic analogy to make it really concrete.
Okay, rewind us.
Let Y be disease burden, maybe average days sick per year in a household.
Yeah.
Let S be the distance of the household from the nearest major city, measured continuously.
Okay, so we might expect disease burden Y to maybe increase as distance S increases. Further from city healthcare, perhaps.
Plausible. So you might see a generally upward sloping relationship on your scatter plot. Now, imagine a new effective health clinic is opened, but only for villages located more than 50 kilometers away from the city.
So 50 kilometers is our S.
RS, exactly. Before the clinic, we just had that smooth upward trend. But after the clinic opens, what do we expect to happen for households just beyond 50 kilometers?
Well, they now have access to this new clinic. So their disease burden Y should hopefully drop.
Right. So on our scatter plot, we'd expect to see the points just to the right of the 50-kilometer line suddenly shift downwards compared to the points just to the left of the line.
Creating that sharp downward jump, that discontinuity right at the 50-kilometer mark.
Precisely. And because we assume households at 49.9 kilometers are otherwise very similar to households at 50.1 kilometers, thanks to the arbitrary nature of the 50-kilometer cutoff, that sudden jump can be interpreted as the causal impact of the health clinic on reducing disease burden for people living near that threshold.
It isolates the clinic's effect from the general trend of distance affecting health.
Exactly. The jump is the program's impact. This visual check is often your first piece of evidence.
It's a really elegant way to leverage that cutoff. Okay, so we've got the core concept. Now let's get into the practicalities. When can you use RD, and how do you actually go about doing it? This means diagnostics and, crucially, checking those assumptions.
Right. This is where the rubber meets the road for you as a researcher. First up, the suitability diagnostic. We've said it before, but it bears repeating. RD is only suitable when your intervention, your program, your policy, whatever it is implemented based on an eligibility criterion defined on a continuous variable S with a sharp cutoff, S.
So if you encounter that kind of setup in your research context, that's your signal. Ding, 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 ding. RD might be applicable here.
That's your first green light. And the very first practical step you should take, even before you run any fancy regressions, is to produce that simple scatter plot we just talked about. Outcome Y versus eligibility S.
And you're looking carefully right around the cutoff S for any visual evidence of that jump, that discontinuity. Is there a noticeable shift in the cloud of points right at the threshold?
It might not always be perfectly obvious, right? Especially with noisy data.
Oh, absolutely. It can be subtle. Sometimes you might need to plot averages within bins of S or run a non-parametric regression line like LOES on either side of the cutoff to see it more clearly.
Yeah.
But a clear visual jump is a strong initial sign that RDD could be effective. If you see absolutely nothing, no hint of a break, well, it doesn't rule out RD entirely, but it suggests the effect might be small, non-existent, or you might have issues with your setup. It's a vital first check.
Okay, visual inspection first. Then we get to the really crucial part, the assumptions. Yes, and like all causal inference methods, 4DD, matching, you name it, RD, relies on specific foundational assumptions. These must hold, and importantly, you need to provide evidence that they hold for your results to be considered valid causal estimates.
This isn't just a technicality. It's fundamental to the credibility of your research, especially at the graduate level.
Absolutely. Fail to validate these, and you're likely just reporting a correlation, not causation. So, assumption number one, arguably the most critical, is the continuity assumption.
What does that mean?
It states that all other relevant variables, especially observable continuous variables, think baseline characteristics. Things measured before the intervention must be continuous across the cutoff S. They shouldn't show a jump at the same point where eligibility changes.
Okay, wait, so the outcome variable Y is supposed to jump at S if the treatment works, but other variables like baseline education or household size should not jump.
Exactly. Why? Because this assumption essentially reconfirms that your cutoff S is truly arbitrary with respect to these other characteristics.
Ah, I see. If other things also changed abruptly at S, it would suggest S isn't just an arbitrary line, but maybe a point where the population itself fundamentally changes.
Precisely. If, say, average household income or average years of experience also jumped discontinuously at the cutoff, it would mean the groups just above and just below S were already different in important ways before the treatment even happened.
Which would completely break the comparability idea. You wouldn't be comparing like with like anymore.
You'd be comparing apples and oranges, and your estimated jump in the outcome Y would be biased, potentially mixing the treatment effect with these pre-existing differences.
So how do you check this continuity assumption?
Two main ways. Graphically, you do the same thing as your initial diagnostic, but for your baseline covariates. Plot each important observable covariate, e.g. age, baseline income, years of experience, against the eligibility variable S. What you're looking for now is the absence of a jump at S. You want to see smooth, continuous relationships for these covariates crossing the threshold.
So a smooth plot supports the assumption. A jumpy plot raises a red flag.
Exactly. A jump in a key covariate is serious cause for concern. The more rigorous approach, often preferred, is regression-based. For each covariate, you run a regression. You regress the covariate on the eligibility dummy, E, 1 if eligible, 0 otherwise, and some function of the eligibility variable S, typically allowing for different relationships on either side of the cutoff. Often, people use SS and maybe interact it with E.
You're basically running a mini RD regression, but using the covariate as the outcome.
You got it. And what you're interested in is the coefficient on that eligibility dummy E. If that coefficient is statistically insignificant for a given covariate, it means there's no statistically significant jump in that covariate at the cutoff.
Which is good news. It supports the continuity assumption for that variable.
Right. You'd want to do this for all your key observable baseline covariates. If they all show insignificant jumps, you gain confidence in the validity of your RD setup.
Okay, that's assumption 1, continuity of covariates. What's the second crucial one?
The second is the no sorting across the cutoff assumption, sometimes called the no manipulation assumption.
And this means?
It means that individuals or units, like households or firms, are not strategically choosing or precisely manipulating their value of the eligibility variable S just so they can fall on one side of the cutoff or the other to get the treatment, or maybe to avoid it.
Ah, so people aren't gaming the system. Like if the income cutoff for benefits is $50,000, people aren't intentionally earning $49,999 just to qualify.
Exactly. Or if a scholarship requires a 3.5 GPA, students aren't somehow managing to land exactly on 3.50 when they otherwise might have been slightly below or above. If they can precisely manipulate their S value around the threshold, the comparison breaks down.
Why? Because those who manage to sort themselves might be different in unobservable ways.
Absolutely. They might be more informed, more motivated, better connected, or just different in ways related to the outcome you're studying. If people can sort, then the group just below the cutoff isn't truly comparable to the group just above anymore, because one group contains these strategic sorters. The as good as random assignment at the threshold is violated.
Okay, makes sense. How do we check for this sorting or manipulation?
The main way is graphical, by looking at the distribution of the eligibility variable S itself, right around the cutoff S. You'd typically plot a histogram, or better yet, a kernel density estimate of S.
And what are you looking for in that density plot?
You're looking for suspicious shapes, right at S. Specifically, you're looking for the absence of any weird clustering or bunching of observations just below the cutoff, if the treatment is below S, and a corresponding sharp drop or hole in the density just above it.
So a sudden spike in the number of people right at the edge of eligibility would be bad.
Very bad. That would be strong evidence of manipulation or sorting. Ideally, you want to see a smooth distribution of S flowing across the cutoff point. No unnatural jumps or dips in the density right at S. There are formal statistical tests, too, like the McCrary density test, which basically formalizes this visual check.
Got it. So continuity of covariates and no sorting manipulation, those are the two big ones.
They are the absolute bedrock. If these hold, you have a much stronger case for interpreting your RD estimate causally.
Okay, with those critical assumptions laid out, let's talk about the different flavors of RD you might encounter.
Yeah.
Because this affects how you actually estimate the effect. You mentioned sharp versus fuzzy.
Yes, that's a crucial distinction for implementation. Let's start with sharp regression discontinuity, or SRD.
Sharp sounds. Precise.
It is. SRD is characterized by perfect compliance with the eligibility rule. What that means is everyone who is eligible based on the cutoff S definitely receives the treatment, and everyone who's ineligible definitely does not. There's no ambiguity, no opting out if you're eligible, no sneaking in if you're ineligible.
So the eligibility rule perfectly determines treatment status. Like that automatic cash transfer example, if your wage was below 30 GHC, you got it, period. If it was above, you didn't, period.
Exactly. Or think of passing a proficiency exam. If the rule is you need 70% to pass, and passing means you get certified, in the treatment, then everyone with 70% or more gets certified. Everyone with 69.9% or less doesn't. Perfect compliance, that's SRD.
Okay, that seems like the ideal, clean scenario. What's the alternative?
The alternative, and often the more common scenario in real-world programs, is fuzzy regression discontinuity, or FRD.
Fuzzy suggests less precision. Imperfect compliance.
Exactly. FRD is characterized by imperfect compliance. In this case, being eligible according to the cutoff S increases the probability of receiving the treatment, but it doesn't guarantee it.
Ah, so some eligible people might not get the treatment.
Right. And sometimes some ineligible people might manage to get the treatment through other means. The eligibility rule influences treatment take-up, but doesn't perfectly determine it.
Can you give an example?
Sure. Think about that soft skills training offered for free to workers with less than 12 years of education, our S. Being eligible, less than 12 years, makes you more likely to attend the training, but it doesn't force you.
Right. Some eligible workers might not sign up. Maybe they're too busy, not interested, don't think it'll help.
Exactly. And maybe some workers with more than 12 years of education hear about the free training and manage to enroll anyway, perhaps if there are empty seats or lax enforcement.
So eligibility nudges participation, but doesn't dictate it? Absolutely. That's fuzzy RD.
That's fuzzy RD. The probability of treatment jumps at the cutoff, but it doesn't necessarily jump from 0 to 1. It might jump from, say, 20% just above the cutoff to 70% just below it.
Okay, that distinction seems really important for how you'd model this. But before we get to the models, one more thing about the setup nonlinear relationships.
Ah, yes. Very important point. So far, when we've talked about plotting Y versus S, we've sort of implicitly drawn straight lines or simple curves. We assumed maybe a linear relationship or perhaps a simple quadratic one.
But real-world relationships can be more complicated, right?
Definitely. The true underlying relationship between your outcome Y and your eligibility variable S might be quite nonlinear. It could be cubic, have kinks, plateaus, all sorts of shapes.
And why does that matter for RD?
It matters hugely because if you don't correctly account for that underlying nonlinear shape, you might mistake the curvature of the relationship for a discontinuity at the cutoff. You could find a jump that isn't really due to the treatment, but just due to forcing a straight line onto a curved reality.
So you need to flexibly model the relationship between Y and S on either side of the cutoff.
Precisely. Your regression model needs to include terms that can capture that potential nonlinearity. This usually means including polynomial terms of the eligibility variable S, like S squared, S cubed interacted with the eligibility dummy E, allowing the shape to differ on both sides of S.
How do you decide how many polynomial terms to include? Is there a risk of overfitting?
There is. That's a classic bias-variance trade-off. Higher-order polynomials can fit the data more closely near the cutoff, reducing bias from misspecification, but can be very sensitive to outliers and lead to noisy estimates, increasing variance.
So what's the practical advice?
First, always look at your scatter plot. Does it look roughly linear near the cutoff or clearly curved? Let the data guide you. Second, standard practice now often favors using local polynomial regressions rather than global polynomials.
Local polynomials, what's the difference?
Instead of fitting one potentially complex polynomial over the entire range of S, you fit simpler polynomials, often just linear or quadratic, but only using data within a specific window or bandwidth around the cutoff S.
Ah, so you're focusing just on the observations very close to the threshold.
Exactly. The idea is that the local randomization argument is strongest right near the cutoff. By focusing locally, you're less sensitive to the overall shape of the YS relationship far from the threshold, and a simple local linear or quadratic fit might be sufficient to capture the trend right near S.
But then you have to choose that bandwidth, right? How wide a window?
Yes, bandwidth selection is critical in local polynomial RD. Too narrow, and you have too few observations, leading to imprecise estimates. Too wide, and you might include observations that aren't really comparable, potentially biasing your estimate because the local randomization assumption breaks down.
So how did you choose it?
There are data-driven methods for optimal bandwidth selection. Procedures developed by Imbens and Kalyan-Urman, often called the IK bandwidth, or Kolonenko, Cattaneo, and Titunic, CCT, are commonly used. These try to balance the bias-variance trade-off automatically. Using these optimal bandwidths along with local linear or quadratic regressions is often considered best practice now. You should also perform robustness checks using different bandwidths, Faraday, half and double the optimal, to see if your results are sensitive to this choice.
Okay, local polynomials and optimal bandwidths, got it. Now let's finally get to the econometric models. Start with sharp RD. SRD. How do we estimate that jump in free?
Right. For SRD, where eligibility E perfectly determines treatment, the model is relatively straightforward. A common specification allowing for different linear trends on either side would be Y plus VOS plus AE plus E plus G plus E.
Let's break that down. Y is the outcome for individual I.
Mhm.
CS is the eligibility variable centered at the cutoff. E is the eligibility dummy, 1 if eligible, 0 otherwise. ESE is an interaction term. She are other control variables, and E is the error.
Correct. The centering, CS, means that Berry represents the estimated outcome for ineligible individuals right at the cutoff, where CS equals 0 and E equals 0.
In Theo, that's the key one.
E pair is the crucial coefficient in SRD. Because A switches from 0 to 1 at the cutoff, EO directly estimates the jump in the outcome Y right at the threshold S. If your RD assumptions, continuity no sorting hold, Bayer's is your unbiased estimate of the causal treatment effect at the cutoff.
And the A term, the interaction.
IS allows the slope of the relationship between Y and S to be different on either side of the cutoff. IA is the slope for the ineligible group, where E0, and Bayer plus IA is the slope for the eligible group, where E1. Allowing for different slopes is generally recommended for flexibility.
And if we suspected a nonlinear relationship, we'd add polynomial terms, like psi S2, and interact those with EI as well.
Exactly. You'd include psi S2, psi S2 EI, and potentially higher order terms if needed, especially if using a global polynomial approach. If using local polynomials with a chosen bandwidth h, the regression is run only for observations where psi s equals h.
Okay, that's sharp RD. Now, what about fuzzy RD, FRD? You said we have imperfect compliance, so E doesn't perfectly predict treatment T, and regressing Y directly on T is biased due to endogeneity.
Correct. That's the challenge in FRD. The actual treatment uptake TI, 1 if they got the treatment, 0 if not, is endogenous. People who choose to take up the treatment might be different in unobservable ways that also affect the outcome Y.
So simple OLS of Y on T gives you a bias estimate.
Right, the solution. We use the eligibility dummy II as an instrumental variable for the actual treatment to.
So RD meets IV. Why is E a good instrument here? We need to check the IV assumptions, right? Relevance, exogeneity, independence, exclusion restriction.
Exactly. Let's check them in the FRD context.
The instrument I must be strongly correlated with the endogenous variable Ti. Does eligibility predict actually getting the treatment?
Well, in FRD, we said eligibility increases the probability of treatment, even if imperfectly. So, yes, they should be correlated. We'd expect E1 people to have a higher rate of T1 than E0 people.
Precisely. That jump in the probability of treatment at the cutoff is what satisfies the relevance condition. You absolutely need to check this in your data. Run the first stage regression of T on E and controls, and ensure E is a strong predictor. A weak first stage is a major problem for IV.
Okay, relevance seems plausible. What about exogeneity or independence? The instrument E must be uncorrelated with the error term A in the outcome equation, Y plus TT plus A.
This is where the core RD logic comes in. Because the cutoff S is arbitrary, the eligibility status E for individuals right around the cutoff is as good as random. It's determined by the arbitrary rule, not by unobservable factors that also affect Y. So the RD setup itself helps ensure the exogeneity of the instrument E locally around the cutoff.
Nice. The RD logic validates the IV assumption. What about the third one, the exclusion restriction?
The exclusion restriction says the instrument E can only affect the outcome Y through its effect on the treatment T. It can't have a direct effect on Y otherwise.
So in our training example, being eligible for training, having 12 years education, shouldn't directly affect wages except by making someone more likely to actually get the training.
Exactly. The eligibility status itself, the piece of paper saying you qualify, shouldn't magically raise your wages. Only the training itself, T, should. This usually holds if the eligibility rule itself doesn't confer some other benefit or stigma.
Okay, so if E is a valid instrument for T, how do we implement this?
We use two-stage least squares, 2SLS. It's the standard workhorse for IV estimation.
2 stages. What's stage 1?
At stage 1, you regress the endogenous treatment variable T on the instrument EI and all the other exogenous variables, including the controls for the eligibility variable S, like CS, polynomials, interactions, and any other covariates xi E. T equals plus E, CS, plus E, plus E, plus E, plus T, plus E.
The key here is S, right? That coefficient on E tells us how much eligibility jumps the probability of treatment at the cutoff.
Exactly. Gies estimates the size of the discontinuity in treatment uptake. It needs to be statistically significant and ideally reasonably large for the relevance condition to hold strongly. From this regression, you then get the predicted values of T. Let's call them thoughty.
That is the part of treatment uptake that's explained by eligibility and the other exogenous stuff, the good variation driven by our instrument.
Precisely. Now for stage 2. You regress the final outcome variable Y on these predicted treatment values, thoughty. along with the same set of controls for S and the other covariates E plus CS plus dot E plus E plus E plus E.
And the coefficient we care about here is...
It steers the coefficient on the predicted treatment theta. This steers from the second stage is the 2SLS estimate of the causal effect of the treatment T on the outcome Y.
And this is unbiased because we've used the instrument E to isolate the exogenous variation in T.
Correct, assuming all our RD and IV assumptions hold. Importantly, this D's in FRD has a specific interpretation. It's the local average treatment effect, S.
Late. What does that mean?
It's the average causal effect of the treatment specifically for the subpopulation of individuals whose treatment status was actually changed by crossing the eligibility threshold S. We sometimes call these people compliers. They took the treatment because they became eligible, or didn't take it because they became ineligible. It's the effect for those induced into or out of treatment by the cutoff.
So it's not necessarily the average effect for everyone who got the treatment, only for those whose decision was effectively determined by the eligibility rule near the cutoff?
Exactly. It's a local effect, both in terms of being estimated at a cutoff S and often in terms of applying to this specific group of compliers. Still, it's a very valuable causal estimate. Alternative way to think about the FRD estimate is simply the jump in the outcome from an SRD regression of Y on E divided by the jump in the treatment probability for the first stage regression of P on E. That ratio gives you the LE.
Okay, that's a lot of methodology, but incredibly useful. Let's make it concrete now with the examples from the source material. First, that sharp RD case, unconditional cash transfer, UCT impact on children's study time.
Right. Context, urban area, developing country, program, automatic UCT for households with wages, equal 30 Ghanaian cedis, GHC, per hour. Goal, increase kids' study time, eligibility variable S, cutoff S equals 30 GHC.
First step, confirm it's sharp RD. The source said automatic, which suggests perfect compliance. How is this checked in the data?
By creating a simple cross-tabulation, you look at the actual UCT receipt, a variable, say, UC feed, CRO if yes, 0 if no, against the eligibility dummy E. E1 if wage equals 30 equals 0 if wage 30.
And what did that show?
It showed perfect compliance. Every single household with EO1 had UC received 1, and every single household with EOSHI had UC received 1. No exceptions. That definitively confirms it's sharp RD.
Okay, SRD confirmed. Next, the initial diagnostic plot, study time Y versus wage S.
Looking at that plot around the 30 GHC cutoff, there was a hint, maybe a slight upward shift in the points just below 30 compared to just above. Not dramatic, but suggestive of a possible discontinuity.
And what about the overall shape, the functional form?
That was important. The plot apparently showed a nonlinear, sort of U-shaped relationship between study time and wage overall. Study time decreased initially as wages rose, then started increasing again.
Which tells us...
It tells us we absolutely need to include nonlinear terms for wage in our regression model to capture that underlying shape. A simple linear fit would be wrong. So including wage and wage squared seems appropriate based on the visual.
Crucial step. Validating assumptions. Let's start with continuity. Did other baseline covariates jump at the 30 GHC cutoff?
To check this, they used the regression-based approach. They regressed key covariates, household size, experience, education on the eligibility dummy E, and the centered wage, wage 30, allowing for different slopes.
And the results.
Excellent news for the RD design. The coefficient on the eligibility dummy E was statistically insignificant for all three covariates, education, experience, and household size.
Meaning no jump in these characteristics at the cutoff.
Exactly. This strongly supports the continuity assumption. It suggests the 30 GHC cutoff is indeed arbitrary with respect to these important household characteristics. People just above and just below are comparable on these observables. Big check mark for validity.
Okay, continuity looks good. What about no sorting? Did people manipulate their wages to be just below 30 GHC?
For this, they looked at the distribution of the wage variable itself using a histogram or density plot zoomed in around the 30 GHC cutoff. Maybe they're looking between 20 and 40 GHC.
Is there any suspicious bunching?
No. The report indicated no strong evidence of clustering or unusual jumps or dips in the wage distribution right around the 30 GHC mark. It looked reasonably smooth crossing the threshold.
So the no sorting assumption also seems plausible here.
Correct. It seems households weren't strategically manipulating reported wages to get the cash transfer. Another check mark for validity.
Fantastic. Both key assumptions validated. So we can proceed with the sharp RD estimation and interpret the result causally. What was the model and result?
Given its SRD and we need the quadratic term, the model estimated was essentially study time, BC, plus median wage plus BOAG plus BOA wage squared plus MIOA per E plus A. Or using the centered wage and appropriate interactions. They likely used robust standard errors too.
And the key coefficient? The coefficient on the eligibility dummy E.
The coefficient on E was statistically significant and positive. The interpretation was that the unconditional cash transfer caused a 4.6-hour per week increase in children's study time, right at the eligibility threshold.
Wow, a specific causal estimate. Because the assumptions held, we can say the program caused this increase.
Precisely. That's the power of well-executed RD. It gives you a credible causal impact estimate, showing the program worked as intended for families near the cutoff.
Okay, great example of successful sharp RD. Now for the second case. Fuzzy RD, the impact of soft skills training on wages.
Right. Context. Free soft skills training offered to workers with less than 12 years of schooling. Goal. Increase wages.
Yeah.
Eligibility variable S equals education, O years. Cutoff S equals 12 years.
The word offered is the first clue it might be fuzzy, right? Implies choice.
Exactly. And confirming this, the cross-tabulation of actual training receipt, T1 if attended, 0 if not, and the eligibility dummy E, E1 if education 12, E0 if education 12, showed imperfect compliance. Meaning not all eligible workers actually attended the training. T was sometimes 0 for them. And importantly, some ineligible workers, EO0, did attend the training. T was sometimes 1 for them. This clearly confirms its fuzzy RD, requiring an IV2 SLS approach.
Okay, FRD confirmed. Initial diagnostic plot. Wages, Y versus education. S, was there a visible jump at 12 years?
Apparently, it was much harder to see here. The scatter plot was noisy, and detecting a clear discontinuity in wages at the 12-year mark was difficult visually. Maybe a slight upward shift, but ambiguous.
And the functional form.
Also tricky.
Yeah.
The relationship wasn't obviously linear or nonlinear near the cutoff. The lecturer in the source material chose to proceed with a linear specification for education in the model, but acknowledged this was debatable and robustness checks would be needed.
All right, now for the crucial part again, assumption validation. Let's start with continuity. Did other covariates jump at the 12-year education mark?
They ran the same checks as before, regressing covariates like household size, experience, and importantly, study time on the eligibility dummy E for 12 years education, and controls for education level around the cutoff.
And the results this time?
This time, a major problem emerged. The coefficient on the eligibility dummy E was found to be statistically significant for the study time covariate.
Uh-oh. That means study time itself shows a discontinuity at the 12-year education threshold.
Yes, and that is a serious violation of the continuity assumption.
Why is that so bad? And why might it happen here?
It's bad because it means people just below 12 years of education, non-high school graduates, are already different in terms of their study habits and likely other unobservables correlated with study habits compared to people just above 12 years, high school graduates, even before considering the training program. The 12-year mark isn't an arbitrary administrative cutoff. It represents a major educational milestone.
High school graduation, that's a big deal, separating people with potentially different skills, opportunities, networks, maybe even different levels of persistence or motivation.
Exactly. So the groups on either side of S12 are not comparable. The cutoff isn't truly arbitrary in the RD sense. This violation undermines the entire basis for a causal interpretation.
Okay, the continuity assumption fails. What about the no-sorting assumption? Did people manipulate their education level around 12 years?
This was harder to assess definitively. Looking at the histogram of education around 12 years, the source material described it as unclear. There might have been some suggestive patterns, maybe more density below 12 than smoothly expected. While people can't easily change past education, strategic dropout before 12 to gain eligibility is conceivable, though perhaps less likely than income manipulation. The conclusion was that this assumption was also difficult to validate convincingly, adding another layer of concern.
So let's summarize the assumption checks for the training example.
Continuity assumption failed due to jump in study time. No sorting assumption. Unclear, potentially problematic.
And the overall conclusion from that?
The crucial conclusion is that the assumptions required for a valid regression discontinuity analysis are not met in this context. The 12-year schooling cutoff is not acting like an arbitrary threshold. It marks a genuine division between different types of individuals.
This is such an important lesson. Just because you have a cutoff doesn't automatically mean RD is valid. You must check the assumptions.
Absolutely. And if they fail, as they did here, you cannot credibly claim your estimate is causal using RD. You'd have to stop, report the failure of the assumptions, and perhaps use other methods or interpretations.
But purely for teaching purposes, the source went through the FRD estimation using 2SLS anyway, right? Just to show the mechanics.
Yes, explicitly warning that the results cannot be interpreted causally, given the failed assumptions. This was just for illustration. They would run the 2SLS model, likely using a command like IVRD2 wage unique education, plus maybe interactions or polynomials, and robust standard errors.
Stage 1, regress training on E and education and controls. Stage 2, regress wage on predicted training hat and education and controls.
Correct. And hypothetically, if the assumptions had held, the coefficient on training hat in the second stage, which was, say, 14 GHC per hour in the example, would have been interpreted as the causal impact of training on wages for those induced into training by the eligibility rule.
But to reiterate one last time,
Because the assumptions did not hold, that 14 GHC estimate is not causal. It's just a correlation, potentially heavily biased by the pre-existing differences between those with less than and more than 12 years of schooling. Trying to pass that off as a causal effect would be fundamentally incorrect.
a stark reminder of the importance of careful diagnostic work. Okay, this has been incredibly thorough. Let's try to wrap up.
We've covered a lot of ground on regression discontinuity. We saw its power as a quasi-experimental method, how it tries to mimic randomization using these arbitrary-seeming cutoffs on continuous variables.
We saw how that allows it, potentially, to identify causal effects by comparing people just above and just below the threshold, controlling for both observed and unobserved factors in that local region.
And we really hammered home the importance of the two key assumptions: continuity of other variables across the cutoff, and the absence of strategic sorting or manipulation around that cutoff. Checking these isn't optional, it's essential.
We also distinguished between sharp RD, perfect compliance, and fuzzy RD, imperfect compliance, and outlined the estimation strategies: straightforward regression for sharp instrumental variables, 2SLS, for fuzzy, often using local polynomials and optimal bandwidths.
And the examples highlighted how critical context and assumption validation are. The cash transfer seemed like a valid RD. The education-based training did not.
Right. So here's a final provocative thought for you, the listener, to take away as you continue your studies and research. The real elegance, the true intellectual rigor of any econometric method, RD included, isn't just in mastering the formulas or running the code.
No, the real craft lies in that painstaking, honest validation of the underlying assumptions. Can you defend the claim that your cutoff is truly arbitrary in your specific context? Can you show evidence that people aren't gaming the system?
As you move forward, always challenge your own setup. Remember that a beautifully complex model built on shaky foundations is ultimately just, shaky. When might that threshold that looks arbitrary on the surface actually conceal some deeper systematic difference? How would you dig into your data beyond the standard tests to uncover that crucial detail?
And what are your responsibilities as a researcher if you find your assumptions don't hold? How do you pivot? How do you communicate those limitations transparently? Answering those questions thoughtfully is what separates good econometric practice from mere mechanical application.
Food for thought. Thank you for joining us on this deep dive.
Thank you.
See you next time.